Hi, this is Dr. John Bergdorf. In this video, we're going to look at tests for similarity of triangles. Theorems you can use to test and show whether two triangles are similar. To begin with, a reminder of what we mean by similar. We're going to talk actually about similar polygons, which is more general. Two polygons are similar if and only if corresponding angles are congruent and ratios of lengths of corresponding sides are all equal. Now, triangles are a type of polygon, so this statement would also be a definition for similar triangles. Two triangles are similar if and only if corresponding angles are congruent and ratios of lengths of corresponding sides are all equal. The big idea of similarity is that similar polygons have the same shape but potentially different sizes. And we can actually see that definition related not just to triangles but to any other polygon, in fact in any other two-dimensional geometric shape. This is the symbol we use for similarity. So if all we had was the definition, and let's restrict ourselves to triangles from this point on, you would have to show that all pairs of corresponding angles are congruent, and that's three sets of angles, and all ratios of lengths of corresponding sides are also equal, and that would be three pairs of sides. That's six things you would have to show. But much like with congruence, there are some theorems that say you can get by with showing less. And so I want to introduce you to these three tests for the similarity of triangles. To show that two triangles are similar, you only have to show one of the following, and they're all abbreviated in nice ways. AA, angle, angle. Two pairs of angles are congruent. Not all three, just two. Side, side, side. Three pairs of one triangle are proportional. That means we're going to be looking at the ratios of lengths of sides. Three sides of one triangle are proportional to three sides of the other triangle. And finally, SAS, or side angle side, ratios of two pairs of corresponding sides are equal, and the included angles are congruent. You might recognize some of these names from tests for congruence of triangles, but they are being applied differently when you're talking about similarity. I have two examples that I want to show you, and they will illustrate two of these theorems, and I think that'll give you an idea that you could use even for the third. So example one, explain why the following triangles are similar and write a similarity statement. Now, let's start on an intuitive level to begin with. I wonder if you would believe me or agree with me if I said that this triangle I'm now sort of tracing in purple has the same shape as the triangle I'm now tracing in gold, even though the gold one is bigger than the purple one. That is the general concept of similarity. I believe those two triangles are similar. But we can't just say that. We have to do something to prove that that is so. So let me talk about how we might do that. I, in particular, believe that these two triangles can be proved to be similar using the AA, or angle-angle theorem. In other words, showing that two pairs of corresponding angles are congruent. Let me show you how easy that is. First of all, I'm given some extra information here that's important. Line segment AB, which is this one right here, is parallel to, that symbol there, in case you haven't seen it, means parallel to line segment DE. So these are parallel line segments. If that's the case, then notice that this side, which I'm going to draw in gold, would be a transversal between two parallel lines, and these two angles, which I'm marking in gold, would therefore be alternate interior angles between two parallel lines. And we know that those are always congruent. So I can immediately say that the angle BAC, that's this one, is congruent, and here's the symbol for congruence, to the angle DEC, and that's this one. And that's because they're alternate interior angles. And I might just make a little bit of a note there. Alternate interior angles, just to remind myself why I knew that was so. So now I need to demonstrate another pair of congruent angles. I only have to do two. I need to clean up this just a little bit, so I'm going to erase a couple things here and see if I can, there, that's kind of what I want to do. The next angles I want to look at are these two. These are vertical angles. Vertical angles are always congruent, whether any other sides are parallel or not. So I can also say very nicely that the angle ACB, which is this one, is congruent to the angle ECD, which is this one. And so I have, and that's because they're vertical angles. So I have two pairs of congruent angles, and that's enough by the AA property to state that these two triangles I had drawn originally are indeed similar. Now notice that the question asked me to write a similarity statement. That's going to be just a statement of the two triangles that I'm talking about and how they're similar. When I do this, it's very important to write the vertices in the corresponding positions. So when I name my first triangle, there's no real big harm there. Just name it any way you wish. Let's say A, B, C. And that's going to be similar to, so we're going to introduce that symbol. The triangle, oops, I'm going to create a space problem here. Let me clear up some room. The triangle below, which has vertices C, D, and E, but we've got to get them in corresponding order. So let's take a look at that. So I would notice that my angle A, which I'm going to just re-emphasize here in the top triangle, is the angle that joins the parallel side and the shorter of the two other sides. So we need to look down in the second triangle to see which angle it is that joins the parallel side and the shorter of the two remaining sides. And I believe that's this one. So we would need to say, we need to describe this triangle first with an E, and then the vertical angle in the top triangle must match the vertical angle in the bottom triangle. So next we'd want to, oh, let's see, that's not what we put next. No, let's go, be more careful. The next angle that I mentioned in describing ABC was angle B. That's the angle that joins the parallel side and the longer, or the middle length of the three sides. So that would be this angle, and it would correspond to the same angle down here between the longer, or the middle rather, we should say, of the three sides and the parallel sides. I believe we need to say that B corresponds to D. And then finally, because I put the C last, that's that vertical angle, and I would need to put C last here. So we would need to say triangle ABC, ABC is similar to triangle EDC, and that's how we would do it. All right, let's do another example. Okay, notice there are no angles mentioned here at all. So if there are two similar triangles in here, we are going to have to use the SSS theorem, where we would look at ratios of corresponding sides. Now notice here that we basically have two isosceles triangles. This one, two sides have length 6 and one side has length 4, and this one, two sides have length 9 and one has length 6. So if I wanted to look at ratios of corresponding sides, what I would want to do is take the length of a longer side from the green triangle over a longer side from the purple triangle, so something like 9 over 6. And notice that the longer side, the other longer side of the green triangle has the same length, and the other longer side of the small triangle has the same length. So those ratios are clearly the same, 9 over 6, 9 over 6. But then you also have to look at the ratios of the two short sides. That would be 6 from the green triangle over 4 from the purple triangle. One thing maybe to note here is when you create these ratios, I think I can safely refer to this as let's say the green triangle and the purple triangle. The numbers across the top, the numerators, all need to be values coming from the same triangle. And those are all measurements from the green triangle, whereas the denominator contains measurements from the purple triangle. You have to stay consistent like that. Are these ratios really equal? Well, the way we would really look at this is we would reduce all the fractions. That's 3 over 2, 3 over 2, and 6 over 4 is 3 over 2. So all ratios of corresponding sides are equal. By the side theorem, we have similar triangles. All we have to do is write the similarity statement, get the vertices in the same corresponding position. What if we start with the non-base angle of one of the isosceles triangles and put it first? So I would refer to triangle T, and then maybe I'd pick one of the base angles, and then the other base angle, and that describes the purple triangle. That's going to be similar to, and when I pick out the vertices from the green triangle, I need to put them in the corresponding orders. So the angle that is not a base angle would go first. That'd be my V, and then my two base angles would be T and U. So triangle TSU is similar to triangle VTU. And I hope those couple of examples give you enough of an idea to see how you apply these similarity theorems to prove whether two triangles are indeed similar.